Good afternoon, sir, and welcome to the meeting.
Yeah, good afternoon. Am I audible?
Yes, sir.
Okay. So I understand we'll start at 3.
Yes, sir. It starts at 3.
Okay. And the participants will be joining and you'll be allowing them, or they'll be just allowed to join on their own?
The participants will be joining through our YouTube link.
Okay. Fine. So it's from 3 to 4.
Yes, sir.
Okay. So I'll also present a screen also. Okay. But initially I'll just talk and then sometimes I'll use the screen.
Sure, sir. Sure.
Yeah. Maybe you can just check whether the screen is visible. You can check now.
Just a second, sir. Yeah.
Hello. Yeah. Okay. So should I wait or I should also exit? I have already joined. I have already joined. Should I exit or I should be there? Okay. Okay. Fine. Fine. Namaste, Narottam Sahuji. Good to see you.
Yes, good afternoon, sir.
Good afternoon.
Namaskar, namaskar.
Great, great.
How are you, sir?
Yeah, I'm good. I'm good.
I hope you and your family and BP family all are fine and in good health,
Yes.
good spirit.
Yes, yes, all are good now. And
Thank you so much.
celebrating this National Mathematics Week. So we started from 15th. So 15th to 22nd, we have a lot.
Yes, yes, you have mentioned.
And you are also part of that.
Yes, sir. Yes, sir. You have mentioned that thing, and in fact, we are very happy to have
Right.
you for our 2-day program. And I think we have arranged this session also live on the YouTube, and
Okay.
all our participants who have registered. So
Okay.
they will be joining through the YouTube, so that in this meet there would be no disturbances.
Okay.
So we have experienced that somebody is muting, unmuting. This is a constant, continuous problem. So we are
Right.
keeping our guest faculty on the main meet link, and all the participants on the YouTube.
Okay. That's great.
So that things. And our colleague Dr. Payal Pandit, she is the scientific officer, research and development. She will be coordinating the session. And today also we are planning the separate program in the evening for this great conjunction where Mr. Jatin is busy on the arrangements. So we are also having this program very interesting, exciting as for the mathematics, physics, and astronomy concerned. So after this session also we'll be joining this great conjunction 2020.
Great.
So thank you so much. I think
Thank you so much for this opportunity given to me. And I know you keep on doing so many programs, so it's great that we keep going.
Thank you so much. I think Dr. Payal can continue the coordination as per the schedule.
Yes, sir. So, very good afternoon to everyone who has joined us in this meeting and through our YouTube channel. Myself, Dr. Payal Pandit, Scientific Officer, Research and Development at GUJCOST. I welcome you all in this webinar session on celebration of National Mathematics Day. National Mathematics Day is celebrated every year on December 22 to recognize the achievements of the Indian mathematician Srinivasa Ramanujan, who was born on this date in 1887. In 2012, our former Prime Minister Manmohan Singh he declared December 22 as National Mathematics Day. Ramanujan lived a short life, but a life which is remembered by many. So I would now like to request Dr. Narottam Sahu sir, Advisor GUJCOST, to give the opening remarks for today's session. Sir. Sahu sir, I request you to give the opening remarks for this session to our participants.
I think you are muted. Dr. Shahu, you are muted.
Yes. So, good afternoon. Welcome, Dr. Rintu Nath, the scientist chief, Vigyan Prasad, Department of Science and Technology, Government of India, and very senior faculty of Vigyan Prasad, and very good colleague of GUJCOST, our science city, and Gujarat. On behalf of GUJCOST, Department of Science and Technology, Government of Gujarat, we welcome you, sir. We thank you for your kind consent, concern, and your participation in this National Mathematics Day program here. We are very happy, and in fact, we are very much impressed with your work as well as your creative that book that you have authored for this occasion, which is very relevant of this occasion. In fact, we are trying to have this copy with all our community science centers and all our science activists and science interns, those who are working in a different, particularly in physics, science, and STEM education and communication in the state. And we'll have a series of activities also. We'll be seek your kind guidance and your support and your available time also, so that we can plan a continuous and a sustainable base of activities, so that it is not like a celebration of 1 day or 2 day. So it would be a part of our activities and curriculum. So we are very much thankful to Begin Prasar also having a collaboration of this program, because as a National Mathematics Day is being planned in a very quick, very systematic way. So many things, because we are here this year also, we are celebrating the 100th year of this great genius mathematician of this country, of this land, who has a very legendary impression and who has very inspiring thoughts and the working cultures for keeping ahead for these young intellectuals. So we hope that this spirit, this work, this type of program, deliberations, interactions, and will be provide that right type of motivation and encouragement for the younger generation to take mathematics as a career, as a choice, as a these things as the subject of their interest, and they can do excel in their career and future. So I once again thanks to all our CSE coordinators also, all our science volunteers, interested mathematicians also, those who are joining this program all across the state from every district through YouTube Live. And we hope that this would be a very learning lessons. And as we have discussed that Dr. Rintunath is very good in organizing these activities in a very interactive way. So we can plan this, because this 2020 gave us a very different types of experience and our these things spirit to our activities. Though this we are going through this challenging pandemic situation, still though there is no limit or there is no less the spirit of our activities and things. Every day, every week, every month, we have different types of programs, activities, engaging ourselves as well as our family, friends, community, our states, everybody in that creative way. So we will be requesting Sir Rintunath sir to help us, guide us to plan for a very sustained base of mathematical activities, which will be good for our STEM-based activities. Sir, we will be very happy to inform you that in addition to our community science centers in all across the state, within a very couple of months, within May or something, this March, after this March, we are in a position to open 3 regional science museums at Rajkot, Patan, Bhavnagar, in a very unique infrastructure in the state and the country. And after 1 or 2 months, we will also, our regional science museum, Bhuj, is also getting ready. So this would be a huge contribution of the state government for the dissemination, promotion of science, technology, and innovation in the states. So 4 regional science museum is being added to our infrastructure, our network within the next couple of months, and we'll have a plan to establish the 5th regional science museum at Baroda, for which we are in the process of acquiring the lands and the other groundwork. So that would be take another 2 years to complete, but by 2021, mid of after March, we'll be adding this 4 regional science museum, which will be giving a huge opportunity, a huge platform for all types of activities. So with this word, I once again welcome Dr. Intunath sir, and I welcome also all the participants in our staff, in our GUJCOST office, as well as our CSC family. I hope this session and this celebration will inspire you to carry out lots of activities in a very innovative way in the coming year. Thank you, and I hope for a very meaningful session and celebration. Thank you. Thank you, sir.
Thank you so much, sir, for this introduction to this webinar. I would I'd be happy to introduce Dr. Nath to all those who have joined us for this session. Dr. Rintu Nath is a senior scientist in Vignan Prasar, an organization of the Department of Science and Technology, Government of India. He did his bachelor's in engineering from Bengal Engineering College, Shibpur, MTech from Central University of Tezpur, and PhD from Central University of Rajasthan. He started his career as a quality control engineer at Samsung and later joined as scientist at Electronic Research and Development Center of India. The research interest of Dr. Nath is data acquisition systems, distributed computing, and cryptography. He is also actively involved in developing and disseminating innovative open-ended scientific experiments for undergraduate students. He has written over 100 popular science articles, books, and research papers. One of his books, Moments in Mathematics, has been a bestseller for several years. The book is translated in Hindi and Spanish. Today he is going to enlighten us on Ramanujan and his legacy. Over to you, Dr. Nath.
Thank you. Thank you all for today's session. It's a wonderful opportunity for all of us to remember Ramanujan. Ramanujan, the great mathematician of 19th century, very short-lived. His mathematical career was only about 20 years. However, the mathematics, for what he has left, is for 200 years. For the mathematicians to ponder on, to think, to work, and to do further research on the mathematics which Ramanujan has left. There are new mysteries, there are new discoveries based on the mathematics what Ramanujan has done. Through my presentation, I would like to give a brief overview of some of his life events, some of the anecdotes, and some of the mathematical concepts which we talk about, why Ramanujan is so important even today, and what are the applications of Ramanujan mathematics. Although it's extremely difficult to explain any of the Ramanujan's mathematics, the high-end mathematics what he did, it's extremely difficult to explain it in a popular term. However, I have selected one or two examples to appreciate you the beauty of mathematics, the beauty of numbers. Ramanujan is also called the magician of numbers. Why he is called magician of numbers? Can we get any insight out of his mathematics? Is it possible for somebody, those who are not mathematically inclined, those who have not studied mathematics at very senior level, can they still appreciate Ramanujan? We should also remember the whole life of Ramanujan itself is so interesting. It is so motivating that all of us need to know the journey of Ramanujan from his school till he was invited by Hardy to Trinity College to do further mathematics. And then the remaining thing is history. So through my presentation, it will be a short presentation. I'd like to tell some of those events. I'm not going to give a biographical sketches, neither is a historical perspective. Only a few, anecdotes, only a few events, few mathematics I have selected so that we can understand, we can appreciate Ramanujan. So I'm going for a presentation, although this we can be. So this is the presentation is Ramanujan and his legacy. Why we need to remember Ramanujan even today. So this is the right hand side. What you see is his famous notebook. 2 pages are given there. Ramanujan, the idea of what he gave, we can consider that as a base of even further mathematics in 21st century. So he did it in 20th, and it's whole 20th century. Many mathematicians did work on that. There are many PhDs even today who are doing the research on Ramanujan mathematics. And the mathematics, what he did at his deathbed, are nothing short of miracles. And nothing short of miracles in the sense that the modern physics, when describing how the fundamental particles interact with each other, is able to get insight from his last writing, that's called Mach theta function. So this is very, very interesting. I'll tell some of those in very, very briefly. So that's why I wrote these ideas continue to shape mathematics, and I should have written mathematics and entire science of 21st century. So these are the school days. So I'll tell you some anecdotes here. As I said, I'm not going as a biographical, perspective, because that's hopefully many of you know it already. So when he was in school, he has shown his ability of mathematical, understanding, and he was different from others. For example, one day, class 11 student came to him and asked him, "Okay, Ramanuj, can you solve it without any pen and paper? Root x plus y is equal to 7, and root x plus root y is equal to 11. What are the integral values of x and y?" And Ramanujan did not take any time. He immediately said it's x, 9, and y, 4. Although it's not difficult, but it shows the mathematical genius in him, that without taking any time, without solving it, actually this equation is not very easy to solve, in fact, because it's not a linear equation. It's not like x plus 3y is equal to 7 and 3x minus 5 is equal to 3x minus y is equal to 9. It's not that. It's a root x plus y. So it's not so simple to solve it, but Ramanujan did it. Another day, it's told that whether it's actually happened this way or not, we do not know, but it's widely believed that the mathematics teacher in school, he was talking about division. So he said, if there are 3 bananas and if I divide by 3 students, each get 1. So he was trying to division method. He was trying to make a generalized equation on on division. And Ramanujan apparently asked the question, if there are 0 bananas and if we divide it among 0 students, still students do get 1. Now this seems to be an awkward question, but it's not. Because 0 division by 0 is having some unique properties. 0 divided by 0 is indeterminate. It's not undefined. Anything divided by 0 is undefined. Whereas 0 divided by 0 is called indeterminate. Why it's indeterminate? Because you cannot get the data value. For example, say the division is inverse of multiplication. So if you say divide 10 by 2, you get 5. So if you multiply 5 to 2, you get back 10. But if you do divided by 0 divided by 0, like you write 0 by 0 is equal to 5. You just assume 5. Now 5 into 0 is 0. So that multiplication rule is valid. Does it mean 0 divided by 0, 5? Then there will be infinite so many solutions. So 0 divided by 0 can be 10. It can be 10,000. That's why it's called indeterminate. And as a young boy, Ramanujan could think about that problem at that early age. He used to recall the numbers, decimal number, the irrational numbers pi, which is a transcendental irrational number, many hundred places after decimal, 3.146, and he will keep on reciting it. So he had that ability. Now, how he used to do it, nobody knows. Whether he used to calculate, whether he used to remember, like pi, e, these values, these are transcendental numbers. And it was very easy for him to actually remember, recite all the numbers after decimal places. First recognition Ramanujan got as his mathematical ability that he received K. Rangathan Rao Prize. There's a spelling mistake prize, sorry, in 1904 in his school. While distributing the prize, headmaster said that Ramanujan's mathematics teacher said that he deserves more than 100 out of 100. Reason being, he's able to solve any questions with multiple methods. So that's how he deserves more than 100 out of 100. And which this was also explained by his fellow students. That yes, Ramanujan is able to do mathematics not in a formal method only, but also in different methods. So most of the students were actually not very comfortable even talking to Ramanujan, thinking that he has some supernatural power. Otherwise, how can he solve those questions like that? This is one of the turning point of Ramanujan, that while at school he got a book from his library. There's a Carr's book, it's G.S. Carr. The book is a synopsis of elementary results in pure and applied mathematics. A synopsis of elementary results in pure and applied mathematics. This has a 6,165 theorem and very short proof, for one line and two line proofs. Ramanujan actually did all this, solved all this, and he actually had a detailed solution of that. Despite having not much understanding of all the, some of these concepts which needed understanding of higher classes mathematics. So he could solve it. Again, it's kind of a miracle how actually he did it. And this has a long-lasting effect on his way of doing mathematics, because he started doing it like only question and then the solution, only answer, no solution, because he used to rub it, he used to raise it. And that's how it started. His notebook is also having all the questions and equations and the final result. But the detailed results are not given. Actually, he did it, but he never bothered to write it down. And he used to, erase all those things. That's how, because, he got first hold of this G.S. Carr's book, and it was only having the questions and only one-liner solution. So he used to do that throughout his life. He used to write mathematical questions for Journal of Indian Mathematical Society, because his stint in Cambridge, Trinity, is mostly known, but Indian Mathematical Society also published many of his questions, although these are not very high-end mathematics, but it is to give as a question answer. The question will be given and then answer will be written later in subsequent versions. So he proposed 58 equations in this Journal of Indian Mathematical Society. Out of 58 he solved. In subsequent issues he solved 39 of those. So some of these beautiful equations are like infinite series, as you see number 1. It's root over 1 plus 2 root over 1. Here I need to tell you, if you are thinking that I'm going to teach you mathematics, please do not think that I'm not going to teach you in mathematics. Neither I'm expecting you to solve it, but some of you may be very interested to see this kind of equations, which is actually a very simple solution. one or two, if you allow me, I'll also try to explain how these equations can come. And it is only needs a kind of a high school standard mathematics. Nothing beyond that. But these are, remember, these are all infinite series. These are all infinite series. Then he asked a question like 2 to the power n minus 7 is a perfect square for the values of 3, 4, 5, 7, and 15 for n. Find other values. So these are the questions he actually gave in this Indian Mathematical Society journal. Then he said the number 1 plus n factorial is a perfect square for the values of 4, 5, 7, and for n. Find other values. He also asked x to the power y is equal to y to the power x. Solve in positive rational numbers. Similarly, he has asked 58 questions. I just picked a few which would be interesting, which would be understood by majority of people. Solution of these first two, is given by Ramanujan on in his volume 4, page 226 of Indian Mathematical Society. Similarly, he gave actually a solution to 39. He did not give all the answer because there was most probably it happened like the journal did not have scope of publishing it anymore, or he left out by the time. We do not know really why it was not published. And not only that, mathematics, infinite series, and highly composite numbers for which Ramanujan is known, but he was also very good in giving questions that are very interesting. Like he asked once, like if a plus b plus c plus d up to infinity is equal to p plus q plus r plus s, and the second equation is a to the power a into b to the power b and so on is equal to p to the power p and c. You solve all the values. Now, how it to be solved? He gave a nice idea. I'm not going to describe the detail, but it has to be solved from the second one first, and then you have to get from second to first. And this is, actually the second equation is actually 1 to the power 1 into 2 to the power 26 to the power 6. Because this 1 plus 2 plus 6 is not equal to 3 plus 3 plus 4, so it was multiplied 1 to the power 1. So that's how you cannot come from 1 to 2, but from 2 to 1. And all of you know perhaps the taxicab number, famous taxicab number 1729, which is the smallest number which can be expressed as cube of two whole numbers in two different ways. So 1729 is expressed as 1 cube plus 12 cube is equal to 9 cube plus 10 cube. This taxicab number apparently looks like it's a mathematical, only for amusement purpose, but it has a greater significance. The further researchers have seen that this taxicab number has indeed potential to go close to Fermat's last theorem. I'll come to that Fermat's last theorem a little later. But taxicab number is not only 1729, which is to be understood in this way, but it has a greater significance as well. Now, this first question which I asked, that some of you, those who are interested, you can think about the solution of this. I'm giving a hint, like if it is x plus 1 whole square, the way I write it, x square plus 2x plus 1. If you take common x from the first two, you get x into x plus 2 plus 1. And rearrange it. X plus 1 whole square is equal to 1 plus x into x plus 2. Why I'm saying so, all these infinite series solutions, the way you find it in normal textbook is actually generic proof. And if it is actually infinity, you take a value of n which tends to be infinity, and then the solution seems to be a bit difficult to comprehend. But if you take some definite values, for example, I've taken 3. Okay, 3 square can be written as 2 plus 1 whole square. Just look at it. 3 square I've written 2 plus 1 whole square is equal to 1 plus x is now 2. 2 into x plus 2. 2 plus 2 is 4. So you can get it. 3 square can be written as 1 plus 2 into 4. Similarly, 4 square can be written as 1 plus 3 into 5. Don't be afraid of seeing some mathematical equations, because I'm told whenever I give kind of a mathematical equations, then viewership reduces all the time. People actually log out. So I've not taken much of a difficult things. I've just taken some very simple things, which anybody with having an mathematical understanding up to class 10 should be able to do it. Those who know only x plus 1 whole square equal to x square plus 2x plus 1. So you'll be able to appreciate. At least one you can try it. You'll be able to appreciate what the infinite series are. Infinite series are not actually infinite always. It has to converge. Now, convergence of infinite series is actually pure mathematical domain, and it needs a rigorous proof whether a series is infinite, is convergent or not. And all the series, all the transcendental number like pi, e, these need to converge. You need to give out output also. And that's again a mathematical beautiful calculations of figures given by Ramanujan, which converges so fast. That's the value of pi. And because the equation is so difficult, I have not included here. But if you are interested, you can, for your information, I can tell you the value of pi for that Ramanujan gave an equation which gives first 5 correct decimal places in the first iteration, and for each iteration next, it gives 6 subsequent digits. And that Ramanujan's equation for pi was actually used in 1987 to calculate 17 million digits of pi after decimal. Only it's yet to be proved whether those all the digits are correct or not. But because it converges so fast, it was used by a supercomputer that time to calculate 17 million digits of pi. So coming to this equation, the 3 square is, from this equation, 3 square can be 3 can be written as 2 plus 1 whole square. So 1 plus 2 into 2 plus 2, 1 plus 4. Similarly 4 square, similarly 5 square. So there's a hint. Now if you take this hint and try to get the solution, I will come to this solution at the end of my session. So you just need to hold it for 20 odd minutes. Another is golden ratio. So many people are actually intrigued about this fine number golden ratio. Sometimes it's given overemphasis for, and almost everything people do try to relate to the golden ratio. I'm not going to that. But I'm trying to tell you the golden ratio, the value is 1 plus root 5 by 2, about 1.6. Ramanujan, during Ramanujan, the name was not known as golden ratio. So there was no concept like golden ratio, but he came up with this. This phi is equal to 1 plus root 5 by 2, and he wrote it as this continuous fraction, infinite continuous fraction. The continued fraction in this red box is exactly the same as what is the blue box. So you cut anywhere, you get the same fraction. Cut anywhere, you get the same one. That's the beauty. That's the beauty of this. The question is, can you construct this, what this equation is? Can you get this solution? Or how did Ramanujan did it? We really do not know how Ramanujan did it, but I will give you some clue. You will see that you can actually construct it, this equation. So you can get this value 1 plus root 5 by 2 by seeing Ramanujan's equation. Ramanujan's equation is extremely difficult to understand here as such if you do not know infinite series. But actually from here, from Ramanujan's equation, you can go to the back calculation, you can get back this value. So again, another open question I'm giving you, I'll solve it at the end of my session. So you have to be with me for 20 minutes in order to get this solution. I'm telling you, my solution will be extremely, absolutely easy solution. Both of these solutions, it's not a textbook solution I'll give you. I'll give you the solution which anybody having understanding up to class 10th mathematics will be able to do it and appreciate it. Now, I got one more question for you. Based on this observed equality, can you set up an equation for the continued fraction and solve it with some elementary algebra? Can you come up with some other values? And at the end of the solution, session, the solution which I'll provide, you'll be able to see that actually you'll be able to provide, get this kind of equations also yourself. Now, after that schooling, we know that Ramanujan is having a very difficult time to continue his mathematics because of he was so poor. You know what happens? One of his friends came and said, Ramanujan, all students and teachers are saying you are a mathematical genius. How do you feel about that? So Ramanujan did not reply. He has shown his, elbow to him, saying that, see the elbow of a genius. So his friend saw this elbow is absolutely blackened, rough, bruised. He said, what happened? What happened with your elbow? Ramanujan said, I write all the time using a pencil in a slate and I rub it with my elbow, and that's how it became. And I do not know, because that's the fastest way I can rub it with my elbow, and this happened. In fact, he used to write on floor also, and he used to rub it. So his friend said, there's so many mathematics you are doing, and people are saying you are actually genius. Why don't you write it down on papers? To that, Ramanujan replied, when food is not available, how can I write on paper? Who will supply me the papers? Because the amount of papers I need in a month is beyond my ability to buy those. So he never wrote it. So all of us actually, we are so unfortunate that his prime writings, mathematics, he actually rubbed it. It was never proved. We do not know how he got all these equations. So during this time, actually, he was advised that you can contact British mathematicians who are in Cambridge about your mathematics. So he wrote later. The first letter was not responded. The second letter he wrote to Hardy, G.H. Hardy. And this letter had 120 theorem. He attached 120 theorem as a representative sample of his work. And after receiving that letter, I'm sure that all of you, many of you know that story, that Hardy actually, first he saw it and then he did not know what to do with that letter. And then again, afternoon, he invited his friend Littlewood to come and join me, and there's an interesting letter came from India, and I am not really sure what to do with that. So both of them sat, and then after some time, they could understand that there's something there. It's not an easy thing, They thought it's maybe somebody mad has written something. Then they actually had many hours to discuss and think about this later. And then Hardy later wrote there in his in a book, they must be true. They must be true mean those theorems, because if they were not true, no one would have had an imagination to invent them. And then rest is history. Then Hardy actually invited Ramanujan to come to Cambridge. And the journey of Ramanujan started in Trinity College, Cambridge. So this is a rare photograph of Ramanujan, who is seen at the medal. Here Ramanujan is. Here in Trinity College also there is one very interesting episode. Ramanujan used to attend Hardy's lectures at Trinity College because Ramanujan did not have the required mathematical qualification, because he had to do higher mathematics. For that he need to have that qualification in mathematics. So he used to attend Hardy's lectures, and one more lecture by Arthur Berry. Arthur Berry was a mathematician. From earlier he used to have with King's College. So one day Arthur Berry was doing some mathematics in board, and he looked at Ramanujan and asked, "Are you listening? Are you to understand?" Ramanujan nodded his head, saying, "Yes, I am with you." But apparently, Arthur Berry, the professor, was not convinced. He asked Ramanujan, "Would you be able to tell me something more than? Will you be able to add anything on it?" Then hesitantly, Ramanujan walked towards the board and wrote the final result, which Berry actually did not do it till that time. Berry would have come to that conclusion at the end of the class, at which Ramanujan did it. So you can understand the surprising that Arthur Berry had that time. There are many more such stories while he was in Trinity College, Cambridge. And that was the time the First World War started. And it was very unfortunate for the world that many of his colleagues, mathematician colleagues, had to join the army to serve. So that is also another important thing, that is, he could not actually get association, coordination, cooperation with other fellow mathematicians much, apart from J.H. Hardy. Of course, Hardy was there throughout with him, but he also developed some, disease there, tuberculosis. It's said that, and which actually could not be cured, and finally he died out of that. But again, it's not tuberculosis, most probably it's some infection of just small intestine, which is curable, but there was no diagnosis of that. So it's a very unfortunate part of that. While he was in Trinity College, Ramanujan published more than 30 research papers in 3 years, 1914 to 1917. And along with Hardy, he developed a new method. It's called circle method to derive an asymptotic formula. And this asymptotic formula was actually given in the first letter what he wrote to Hardy. And there are implications of Ramanujan's mathematics while he was in Trinity College. One of them is the Goldberg's conjecture and other additive questions which was derived out of Ramanujan mathematics. He had a great contribution in composite numbers. And this composite number, his contribution in composite numbers, are given many more research areas in 20th century mathematics. One of his landmark papers is on certain mathematical functions. He did Fourier coefficients of modular forms. At the time, the theory of modular form was not even developed. However, the major contribution is said to have these three fundamental conjectures that serve as a guiding force for the development of the theory. The first two conjectures led to the development of what is called Hecke theory. And this Hecke theory is now used in physics. And not only in physics, the Fermat's last theorem was solved by Andrew Wiles in 1994. Now, what is Fermat's last theorem is, if it is x to the power a plus y to the power b is equal to z to the power c, then there is no solution if a, b, and c more than 3. And it was solved mathematically, although it seems to be very easy, but it's not. If you see that what Andrew Wiles said, some mathematics problems look simple, and you try them for a year or so, and then you try them for 100 years. And it turns out that they are extremely hard to solve. There's no reason why these problems shouldn't be easy, and yet they turn out to be extremely intricate. Fermat's last theorem is most beautiful example of this. So those who are interested, you can go through this, what is Fermat's last theorem. As I said, it's x to the power a plus y to the power b is equal to z to the power c. There's no solutions if a, b, c is 3 or more than 3. There's no solution. And surprisingly, Ramanujan actually proved the way it actually reached this Fermat's last theorem proof. Because he got many equations which is in the form x to the power 4 is equal to y to the power 4 plus z to the power 4 plus 1 or minus 1. So he got that level. So that means no solution more than 3 and more was possible. Many of his equations suggest that. Third conjecture created a sensation. It played a major role in formulating Lagrange's program, a far-reaching program articulated by Lagrange by 1970s. And for that, Lagrange was awarded Field Medal. Now, Field Medal is actually equivalent, Nobel equivalent of mathematics, because Nobel Prize, there is no Nobel Prize for mathematics. For mathematics is a field level, which is field medal, which is considered to be equivalent to the Nobel Prize. Now, after his initial spell in Trinity College, he actually, because of his health deteriorated, he returned India, and his health continued to deteriorate. And during his deathbed, he did very intrigued mathematics, and he wrote a letter to Hardy in 1920. He talked about mock theta function, and he gave 17 examples of this new function. Now, that time theta function was known, but mock theta was nearly similar to mock theta function. Mock theta function nearly similar, but not exactly same as theta function. And this mock theta function was largely ignored. From 1920s to 1987, this mock theta function was ignored. And because the mathematician could not prove it, it was only, Ramanujan only gave a solution without a thorough proof. So he just gave the result. So unifying conceptual framework was missing. That's how it was, no mathematician could understand that till late 2002, when this mock theta function is widely accepted as in physics, how the fundamental particles interact with each other is also used in understanding how the universe works. And it's a principal part of many other physical phenomena, including string theory. The framework was discovered only recently in 2002, and it is told that the mathematics done by Ramanujan and whatever has been understood till now is only tip of the iceberg. And obviously, we can say that Ramanujan knew much more than he revealed. In 1987, I read the quote, it's very important. Freeman said that the mock theta function gives us tantalizing hints of a grand synthesis still to be discovered. It should be possible to build them onto a coherent group theoretical structure. This remains a challenge for the future. It was predicted in 1987 and 2002. It came to be true. The recent advancement in the theory are just foreshadow of great things to come. As I said, most of this interdisciplinary research, especially in physics, the way fundamental particles interact, string theory, black holes, many of these physical theory are based on something which is very close to this mock theta function. And this is going to give direction for the future, not only in mathematics, but all the interdisciplinary applications. Now the question, as I said, that how did Ramanujan discover this theorem? Because as I said, there is no formal proof of many of these theorems. But to which I would like to quote what Hardy wrote. Quote, "It was his insight into algebraic formula, transformation of infinite series and so forth, that was most amazing. On this side, most certainly I have never met his equal, and I can compare him only with Euler or Jacobi. He worked far more than the majority of modern mathematicians." To this, it's Hardy has written many more about Ramanujan. Although it's been told that Hardy was his mentor, but Hardy once said that the greatest discovery I have done ever is discovering Ramanujan. So that shows that the kind of relationship, the kind of regard Hardy was having for Ramanujan. There are few more anecdotes I would like to tell you. Few more stories, very interesting stories. This is all based on his Ramanujan's familiarity about mathematics and this number theorem. That time, when Ramanujan is in Trinity College, that time P.C. Mahalanobis, this famous statistician, he was also in Trinity College. So his professor said that Ramanujan, mathematician from India, has come here. Have you met him? Now Mahalanobis knew about Ramanujan and he wanted to meet him, and he actually planned and met him. So when he went to Ramanujan's room, Ramanujan was so happy that to get one person from India. So he said that, okay, I'll be offering you lunch today. So he started cooking. That time Ramanujan was going through a magazine which was there, and then there was a mathematical puzzle on that. This puzzle, I'm not describing the puzzle. It's it's a big puzzle, but he solved it. Ramanujan solved it, and then he was telling Ramanujan, see, I solved this puzzle, but I'm not happy because it's a trial and error. Trial and error means he did not get an equation done, but he actually put values and then tried to see whether it matches it or not. So, but I think it's something more than this should come. You are a mathematician, will you be able to interested? But as you're cooking now, maybe we can discuss it later. To this, Ramanujan said, I'm cooking with my hands, I can still think. You tell me the problem. Then he said, and immediately Ramanujan said that there are infinite solutions possible, and then gave one equation, again this infinite series. This is amazing to see that how Ramanujan used to think so fast, as if he knew the problem already, and the solution was there in his brain already. Now, the Nobel laureate Subramaniam Chandrasekhar once wrote long about this Ramanujan, especially once he got his Nobel Prize. I'm not reading the entire thing. I'm just underlining something. I can't still recall the gladness I felt and the assurance that one brought up under circumstances similar to own could achieve. That is, he's talking about under the astonishing surprise, way that Ramanujan could do mathematics from poverty, from other, his health, everything he could overcome, and he could come to the greatest, the peak of the mathematics within a short time span. So obviously we can say that Ramanujan knew much more than he revealed. And as long as the spirit of inquiry is alive, legacy will pass from one generation to the next. Now coming to the solution, those who are listening to this, the solution of first question is 3. Now see how it comes. X plus 1 whole square, that hint was given earlier also. So which is x squared plus 2x plus 1. Now rearrange this term this, so you get 3 squared is equal to 1 plus 2 into 4. This is 3 squared is 2 plus 1, so 1 plus 2 into 4. Similarly, 4 should be written as 3 plus 1. So 3 plus 1, that's 4 squared is equal to 1 plus 3 into 3 plus 2, 5. So this is, and so on. So write it down. So you get 3. So 3 can be written as. So think about 4. How to write 4? That's what I said. That these solutions, because I have taken smaller numbers, you will be able to understand this. And this converges. You can actually check it. Take out, truncate any part, and you'll get the value which will be very close to 3. The more number of times you solve, you get more closer to 3. So this is the infinite series. However, it's converging. It will converge to 3. Similarly, you can try for 4. You do it yourself, and you get 4. In fact, the 4 question, the solution to this was given initially when I wrote it. That when he wrote it to Indian Mathematical Society, question number 2 was for 4. Now coming to golden ratio, this one. This is a solution to puzzle 2. This equation, this is infinite series, is exactly it's a self-similar. So any part is similar to the bigger part. Smaller part, all smaller parts are similar to bigger part. This kind of equation can be always written as 1 plus 1 by x. See? So if you take entire thing is x, and because the smaller part is equal to bigger part, the solution has to be also x. Because this blue part is equal to red part. The red part solution is x. So x can be written as 1 plus 1 by, again this part is x, because it's similar. Smaller part is similar to bigger part. So x is equal to 1 plus 1 by x. Try solving this. As I said, those who have 10th level mathematics should be able to solve this x square minus x minus 1 equal to 0, and you get the surprisingly solution 1 plus root 5 by 2 and 1 minus root 5 by 2. And this is what the golden ratio, because the negative value is to be discarded because golden ratio is a positive value, 1.6 something, 1.62, and it keeps on going because it's a rational number, irrational number. So 1 plus root 5 by 2, if you solve it, think about some other equations also and see what value you get. You may not get golden ratio, but you get some other ratio. So, although Ramanujan mathematics is beyond the comprehension of common people, but by looking at his life of mathematics and at least trying to understand some of the simple series, infinite series, what he did in the school level. Remember, this mathematics he did in school. It can definitely give us an insight of how great Ramanujan was. What is the profound implication of Ramanujan's mathematics in even now and the generations to come, and what we should know about Ramanujan so that we get motivated, and why Ramanujan is so important even today. So that's it for today's session. Thank you all, those who have joined us. I do not know whether can we take questions or not, because I'm not sure that how many of you are online. If there are questions, I'll be happy to answer you. Otherwise, my session is over now. So I've just stopped sharing.
Yeah, thank you so much, sir, for this very nice session. The taxi cab number and the golden ratio and other episodes, his life at Trinity, and those have been really interesting ones. And I see that on our YouTube channel we have students and our community science center coordinators who are there. So if you have any questions, you may post it on YouTube. I can take it up from here in the session. And yeah, so Ramanujan genuinely lived a very short life, but a very fulfilling life. And I read that he was the youngest fellow in the history of Royal Society.
Absolutely,
And
yeah. I missed out that point. You are very right. He was the youngest fellow of Royal Society of London.
yeah,
Thank
yeah,
you for
and
sharing this information.
yes, for and so the students who have joined us in this session, I feel that the sky's the limit and anything is possible. We can see it from the life of Ramanujan, which was very short. He lived hardly 32 years of life, and still he achieved a lot that we remember him to this day. I think, yeah, so as of now, we don't have any
No problem.
questions.
Anybody
But
who is willing to contact me, my contact email ID can be given to them so that they can contact me. Intentionally, I've given 2 questions, 2 open-ended questions also for students, those who are interested to solve it.
yeah,
Because I try to tell you that whenever we listen about Ramanujan, normally we only listen to his life stories, and we do not try to understand or appreciate the mathematics what he did. So my whole idea was to give a fine balance. Of course, this life of Ramanujan is very motivating. All of us should not to know, but also to give 1 or 2 questions so that we appreciate Ramanujan's mathematics and to understand how we can also contribute whatever high school mathematics knowledge we have, and if somebody is having any as per, they want to go for higher studies in mathematics, how you can actually take some lesson from Ramanujan's notebook. There are many other things. So those infinite series are to begin with. So I've given 2 questions. Those who are interested to solve it, you can solve, and you can interact with me, and you can send your solutions to me also. I'll be ready to answer it, and if anything I can contribute for that, I'll be very happy.
Yeah, thank you so much, sir. I think our students who have, yeah, I have one question here. I want to know what was the concept about infinity.
See, infinity, both the equations I have given, those are infinite series actually, there's never ending, but infinite series are converging also. Infinity does not mean in mathematics that it cannot converge. Infinite series are mostly it has to converge. All the series what Ramanujan wrote initially, like you can write 3 is equal to root over 1 plus root over 2 plus root. This is infinite series. There are infinite fractions also. That's the golden ratio. X is equal to x plus 1 by x is a arithmetic equation for an infinite series. So infinite series. Ramanujan was especially intrigued with the infinite series, and his many of these contributions are in infinite series.
Yeah, thank you, sir. Yes, so the students can post this whole video is available on our YouTube channel. So students can go through that once again also and try to answer the questions which are posed by sir and try to solve it and send it to him. You can also contact him over his email and I think somebody is still posting. Sir, is minus 1 over 12. What does it show?
Can you repeat the question?
Minus 1 by 12. What does it show? I'm not very clear about what he has written in
Minus 1 by 12 is minus 1 by 12. I mean, I don't, maybe I'm not able to understand the question.
Yes, it's not very clear. Yeah, so I think they can post it on our
You can share
to
me
our
those
office and we can
questions.
pass it on to you, sir. So I thank you so much for this nice session and thank you for joining us and sparing your valuable time. And we are sure we will be keeping in touch with you for
Thank you.
our.
Thank you very much. So I
Yeah.
sign off. Yeah.
Okay, sir. Bye. Have a good day, sir.